Today, we're diving into the incredible world of transition metals, a special group of elements that are behind everything from the color of gemstones to the way your body uses oxygen to the engines of industry. It's going to be a fascinating ride. So, let's start with a little riddle. What do these three things have in common? You've got the deep red of blood, the stunning blue of a sapphire, and, yeah, that catalytic converter under your car. They seem completely unrelated, right? But believe it or not, they are all connected by one amazing chemical secret. And that secret is transition metals. Now, the official definition is a bit of a mouthful. A D-block element that forms one or more stable ions with a partially filled D subshell. Okay, I know, that sounds super technical, but stick with me because that last part, that partially filled D subshell, is the key to unlocking everything that makes these elements so unbelievably cool.
So here's our game plan. We'll start by looking at what makes these metals so important in the first place. Then we'll dive into their most famous trait, their colors. We'll uncover the electron secret that makes it all possible, see them in action with a real-world example, and then wrap it all up with why this stuff truly matters.
All right, first up, let's talk about what makes these metals the true workhorses of our modern world. So, what sets these guys apart? Well, for one, they're tough. Unlike softer metals you might know, things like iron and titanium are incredibly strong, with super high melting points. That's because their atoms are packed together really tightly. But where the real magic happens is in their chemistry. They are amazing catalysts. They speed up chemical reactions without getting used up themselves. And they can form these beautiful, intricate structures called complex ions. Now for the really fun stuff. Let's talk about their most famous characteristics. And honestly, it's best to think of them not just as properties, but as chemical superpowers. So, superpower number one, they're absolutely brilliant colors. I mean, think about it. The bright blue of copper sulfate, the rich green of nickel salts, the deep purple of potassium permanganate. They literally paint our world. But why? Why aren't they all just a boring silvery gray like so many other metals? And here's the secret sauce. The color comes from that partially filled d orbital we mentioned earlier. It's the golden rule. If that d orbital is totally empty, like you see with scandium ions, or packed to the brim full, like with zinc ions, then its compounds are usually just plain white or colorless. All the action, all the color happens right in the middle. Okay, on to superpower number two. These elements are basically chemical chameleons. They can shapeshift, existing in a whole bunch of different oxidation states. Really, all this means is that they can lose different numbers of electrons, which gives them this incredible versatility in reactions. And just look at this. This table shows it perfectly. Check out manganese. It can have oxidation states from +2 all the way up to +7. That is just wild. And iron's ability to just flip-flop between its +2 and +3 state, that's not just a neat party trick. It's absolutely essential for how hemoglobin carries oxygen in our blood. This is the chemistry of life itself. So we know what they can do. But to understand why they have these incredible superpowers, we have to get a little nerdy and unlock their secret code. And that means looking at their electrons. Okay, let's build an atom. The basic rule, the Aufbau principle, says that electrons fill up the lowest energy spots, or orbitals, first. But here's where things get a little weird, a little quantum. The 4s orbital is actually at a slightly lower energy level than the 3d orbitals. So counterintuitively, electrons fill up that 4s orbital before they start popping into the 3d. It's a tiny detail, but it changes everything. So here's the playbook. Fill from the bottom up. Remember that 4s comes before 3d. And when you get to those 5d orbitals, electrons like their personal space. They'll take an empty orbital before they double up. Simple enough, right? But like any good story, this one has a couple of rebels. And here they are, chromium and copper. See, atoms are all about one thing, stability. And it turns out that having a d orbital that is exactly half full with 5 electrons or completely full with 10 is an extra stable, kind of zen state for an atom. So to get there, both chromium and copper promote one of their 4s electrons up to the 3d level. They break the rules to find a little more peace. All right, we've got the electron code figured out, but what in the world does this have to do with those amazing colors we were talking about? Let's connect the dots. So, when a transition metal ion is just floating around by itself, all 5 of its d orbitals have the exact same energy. But when other molecules, chemists call them ligands, get close, they cause a ruckus.
They interact with those orbitals and cause them to split into two separate energy levels, a lower energy group and a slightly higher energy group. They're not all equal anymore. And that tiny energy gap that forms, that is everything. Because when white light shines through, an electron in one of those lower orbitals can absorb a very specific packet of energy, a specific color of light, to make the jump up to a higher orbital. So, if it absorbs, say, the orange-yellow light, that light is now gone. What's left to pass through to your eyes? The complementary color, blue-green. And that is the secret to their color.
Okay, this is all fascinating theory, but let's put it into practice. Let's see how we can actually use these unique properties to solve a real-world problem. So here's our challenge. We have a piece of steel, and our job is to figure out exactly how much iron is in it. Sounds tricky, but we can do it with a really clever and visual technique called a redox titration. And what's so cool about this is that it perfectly combines the two superpowers we've been talking about. We're going to rely on iron's ability to change its oxidation state, and we'll use the intense color of another transition metal ion to tell us exactly when our reaction is done. Here's how it goes out. First, we dissolve the steel in some acid. This gives us a solution full of iron 2 ions. Then we slowly, drop by drop, add a deep purple solution of manganate ions. As each purple drop hits the solution, it instantly reacts with the iron and becomes colorless. So you keep adding, drop, 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 watching the purple vanish until the very last bit of iron is used up. The next drop has nothing to react with, and the whole solution turns a faint, persistent pink. That's our signal. We're done. And by knowing exactly how much of the purple solution we added, we can calculate the amount of iron down to the milligram. Pretty neat, huh? So let's zoom back out. We've seen their crazy colors and their clever chemistry. But why are these elements really so crucial? Why are they the unsung heroes of our world? Here's the main thing to remember. That messy, partially filled d orbital, the very thing that makes them seem a bit unstable, is actually the source of all their power. It's what gives us the vibrant colors for paints and gemstones. It's what allows for the complex chemistry of life, like iron in our blood. And it's what makes them such powerful catalysts, driving entire global industries forward. In the end, what looks like their biggest flaw, their instability, is actually their greatest strength. It really makes you wonder, doesn't it? Where else are these incredible elemental chameleons hiding in plain sight, quietly making our world work?